Take a look at this idea of derivative at a point in action. Here's a function. F of x equals x squared minus 3x minus 4. One thing that you'll find is useful throughout the year is to be able to quickly visualize a function when you can. In this case, we can. It's a parabola. So just think through what it would look like. We know that it's x squared, so it's upward facing. If you do a quick factoring job in your head there, it's x minus 4, x plus 1. So there'll be an x-intercept at 1 and 4, a y-intercept at negative 4. And even if you're not very precise here, the quick, or pretty for that matter, the quick visualization definitely goes a long way to making things make more sense. So we're going to use the definition of derivative at a point to find f prime of 3, and just a quick visualization of what f prime of 3 means, it would be, like we said in the last video, the instantaneous rate of change when x is 3. Well, when x is 3 on this function, the point is actually 3, negative 4. It's worth taking a quick second just to figure out what that would be. That's 9 minus 9 minus 4. What we're talking about when we talk about f prime of 3, we're thinking about the instantaneous rate of change when x is 3, which would be visually the slope of this tangent line. Not the tangent line itself. Very important. A tangent line is not a derivative. They're not synonyms. The derivative is the slope of that tangent line, the instantaneous rate of change. So if we wanted to find the slope of that tangent line, we could use the definition of derivative at a point. I'll write the definition above up here. F prime of c is equal to the limit of f of x minus f of c over x minus c as x approaches c. And I want you to quickly notice the 4 times that c appear in this definition. Well, if we're talking about f prime of 3, that means that all 4 of those are going to be 3's, because we're talking specifically about the instantaneous rate of change when x is 3. So that would be the limit of f of x minus f of 3 over x minus 3 as x approaches 3. So all 4 of those c's became 3's, or we're talking about when that constant is 3. We do need to do a little bit of substituting in. So f of x we know is x squared minus 3x minus 4. And we just figured out that f of 3 was negative 4. So we'll subtract that at the end. And it shouldn't come as a surprise, really, that we get this x minus 3 in the denominator, which we know is going to give us trouble if we're trying to take the limit as x approaches 3, but we kind of already knew that was going to happen. The whole point of this exercise is we knew there was going to be trouble because we're talking about finding the difference between 2 points when we only have 1 point. So of course there's going to be problems somewhere, but luckily we learned how to deal with those problems by using the very quick strategy for evaluating limits that take on an indeterminate form. We're going to factor. It'll cancel. Things will be easy. Let me just do the subtraction here. The negative 4 minus negative 4 cancels. Notice how I still have that limit notation, because even as I work on simplifying what's inside the limit, I still haven't taken the limit yet. And now I can cancel. I expect you to be able to factor in your head. And so if you don't write out this step, the limit of x times x minus 3 over x minus 3 as x approaches 3, and you skip right to this next one, the limit of just plain old x as x approaches 3, that's fine. This step in here, that's optional. Like, I don't really expect you to need to write that down. If it helps you to see what you're doing, no problem, it's great. But if you skip that, that's fine too, because that's working on algebra. It's the next step, doing the limit by plugging and doing the direct substitution. That's calculus that you can't skip over. So f prime of 3 is equal to 3. And I want you to pay attention to this question that I asked down here. How does this make sense looking at that graph? Well, remember what we're saying f prime of 3 is. The instantaneous rate of change, or visually, the slope of the tangent line. Well, yeah, this right here looks like a line with a steep slope. Sure, 3 sounds believable. It's positive. That's a big giveaway that we're on the right track. Had we gotten a negative answer here, that would have been a problem. That would have been trouble, because we can see by looking at this graph that we're expecting the slope of that tangent to be positive. It's not like a very shallow line like that, which we know would have had a slope, of a half or a third or something like that. So we're in good shape. Okay, moving on. And like I said a minute ago, there's a big difference between the line, that blue tangent line, and the derivative, which is the slope of that tangent line. Those are two very different things. What I ask you for next in part B is to actually write the equation of that tangent line. Notice we haven't done it yet. We know the slope of the line is 3, but we don't know the equation of the line yet. However, it's very easy to get when we think in terms of point slope. So generally, a quick reminder of point slope form of a line. You learned it in Algebra 1 and Algebra 2 as y minus y1 equals m times x minus x1. But I'm going to change things up for calculus. If you keep pulling back to that form, that's fine. Be my guest. But it'll be a little bit helpful if you can get used to thinking about it using the notation we use in calculus, where instead of m, we would actually use the notation for the slope itself, which we know is f prime. And instead of x1, y1, we don't often use that in calculus. Well, we gave that coordinate a name already also. That point was c, comma, f of c. And the slope is f prime of c. That's a point of tangency and the slope of the line of tangency. So we can just use those symbols instead. Instead of y1, I'll call it the y value of my point. And instead of m, I'll call it the derivative at my point. And instead of x1, I'm going to use the constant. So if you kind of remember this, it's the same thing as point slope form. It just uses the notation that we'll have already used in the problem, so it makes it really easy to plug numbers in, if you can remember it. And so this equation for the tangent line is y minus negative 4, because remember that was f prime of 3, equals, I'm sorry, that was f of 3, not f prime of 3. F prime of 3 is the slope. We saw that was 3 times x minus 3 itself. And so that's the equation of a line. Leave it like that. If you insist on getting y by itself because old habits die hard, be my guest. You are certainly welcome to move that 4 over. Don't waste your time putting it into slope-intercept form. That doesn't do you any good. And honestly, I advise you just leave it as point slope. Okay. One last thing I want to show you on this video. There's an idea. So you might be asking, like, all right, what good is all this for? Like, what does this mean to me? So one thing that you can do with this idea of the derivative at a point, or the instantaneous rate of change, is an idea called local linearity. So I'm going to go back to that parabola I drew. I'll resketch it quickly right over here. And remember, we are talking about when x is equal to 3. And perhaps didn't draw it quite stably enough, but there's the line here. That's the tangent line. What I want you to notice is if we zoom in, and it's harder than it looks, and zoom in, that's as far as I can get, for a brief moment in time right here, right around that point of tangency, the orange line and the blue line really do seem to overlap with each other. As long as you can find the derivative of a function, around that point, the point where you have found the derivative, we say that the function has what's called local linearity, where for just the briefest instant in time, it's kind of just like a straight line. And so one thing you can do with that is use the straight line, whose equation we just found, and it wasn't all that hard. Y plus 4 equals 3 times x minus 3. If I want to find f of 3.14, which is kind of an annoying number. If you imagine, it's not the end of the world if you have to do this, but plugging that into x squared minus 3x minus 4, that's annoying to square 3.14. Much, 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 much easier to plug it into a linear function. And so the idea is that even though that blue line isn't exactly following the orange line, there's like a little bit of separation here. It's close enough to make a good estimate. So if you wanted to make a pretty good estimate for f of 3.14, instead of plugging it into the annoying 3.14 squared minus 3 times 3.14 minus 4, you plug it in for this x instead. And so we'll say y plus 4 is equal to 3 times 3.14 minus 3, and this is just a lot easier. Y plus 4 equals 3 times 0.14. Y plus 4 equals 0.42. And so y is equal to, I should really be using the approximately sign, but that's okay. I'll finish doing it this way, and then I'll put that in. 3.58. Negative 3.58. So I can say that f of 3.14 is approximately negative 3.58. That is one use for the derivative. It's to treat a curved line as if it were straight, just for the sake of estimating y values for x values that are a little bit inconvenient to plug in.